Okay, welcome back. And for the rest 1.5 hour, we're going to use this another notebook called Bayes for Simple Models. And I think you can safely run through the first two blocks. It doesn't contain any very important message. And then let's start directly from this text. So this exercise will apply the emulator-assisted Bayesian parameter estimation to a very simple model for bulk physics. So the bulk models in initial, so bulk models that contains both initial conditions, dynamical models, will be go over tomorrow. So in JETSCAPE, the initial condition is taken care by the Trento initial conditions, and the dynamical models include pre-equilibrium evolutions, hydrodynamic evolutions, and also particle addition plus hadronic scatterings and decays. But if you make that abstractions, this dynamical models is basically tells you how the observables responses to first of all the initial conditions and also to other physical parameters like shear viscosity and bulk viscosity that governs the evolutions. So we're not going to use the full models in this first exercise in this simple exercise, but still our target quantity is the shear viscosity as function of temperature. Actually, we're going to use the same temperature-dependent parameterization for the shear viscosity as the recent JETSCAPE publications. So eta over s as a function of t, we're going to parameterize as piecewise linear functions. So if t is greater than some critical values d, it has a slope the b parameter as its slope. If below the certain temperatures, there's a kink at t equals to d, and then switch to another slope c. And at this d function, the value of the kink is the a parameter. And although this model is very simple, I want to pass a very important message is that often in the physical models, we don't really have infinite accuracy or sensitivity to any details of this unknown functions. So usually the hydrodynamic evolution, for example, or some other evolution model you're going to encounter in the future, they're only going to sensitive to a certain integrated or coarse feature of a function of input. So that's why in constructing this very simple bulk models, we will first define a so-called effective shear viscosity. And this effective shear viscosity, the idea is I directly take from this literature. You can check out what was the reason that why we're defining quantity like this. So basically, we take the temperature-dependent shear viscosity and average over temperatures. And this is a weighted average controlled by t to some other powers. Right now, we're going to assume p equals to 1, p equals to -1 just for now. So you kind of get the eta over s at high temperature to be less important than the eta over s at low temperatures. So this is also qualitatively the case in realistic models, because when you have very fast, for example, really expansions, the initial temperatures drops really fast, so the hydrodynamics don't spend a lot of time in the high temperature regions, and later when the expansion slows down, that's where most of the hydrodynamics spends. So that's kind of qualitatively tells our model that we're only going to sensitive to a certain temperature region of this original functions with full details. And then we will use some kind of like acoustic scaling models that translates the initial energy densities into final charge particle multiplicities. And you can, for example, also have some viscous heating effect. And the V2 will translate, and the simple model will translate initial centrality averaged eccentricity vector epsilon2 and decay it by this effective shear viscosity over the multiplicities to get the V2. So it's just a very simple model, but it kind of gives you the qualitative feature output we'll see in the data. So one qualitative feature is that the V2 and how V2 and charged particles are correlated with the shear viscosities and how the uncertainties in the normalization will affect the extraction of the shear viscosity. So that's basically the two features we try to include it in this simple model. And in total, it will introduce 5 parameters. So this will be a first time that we encounter a high-dimensional parameter space. So there's a normalization that converts initial energy density to final charge particle multiplicities, and the A, B, C, D parameters that parameterize this piecewise linear functional form. Okay, and as I said, for now, we're going to set this p power equals to -1. And the integration range, the lower bound of this integration is 160 MeV, or in this case, in units of GeV. And now if you run to the second block, it will load a pre-generated data from Trento initial conditions, but this is not event by event informations. Rather, this is the unnormalized energy density and unnormalized average initial temperatures from the initial conditions as a function of centralities, and also the event averaged epsilon2 vectors as a function of centralities. And that simple model will take these quantities and transform them into what we call observables. Okay, this is just for display. And in block 3, this is the final block where we set up the model. So this sets up the initial condition, and here is the dynamical model. This first function defines eta over s as a function of temperature, and this second function will compute the effective eta over s as we defined. It's basically a temperature average of the shear viscosity. And finally, this is the toy model that takes parameters normalization A, B, C, D, and then returns the predicted charge particle multiplicity and V2 as function of centrality. And finally, it's just an example to show you what this function looks like, this eta over s looks like. So you're free to change the parameters over here, and then to plot you this piecewise linear. For example, right now I'm choosing the minimum or the kink value of eta over s is 0.1. The high temperature slope is 2, and the low temperature slope is 5. And the location of the kink is at 0.2 GeV, and that's what you get. So so this function form is quite flexible. You can change the kink to 0.5. And you can also make the slope negative, and it will be cut out at 1 meter or else try to drop below 0. It would be cut out at 0. Okay. Now I'll set it back to start with. Okay, now this up to this point is just setting up the model, which is only designed for the purpose of this notebook. And from here we're going into the major workflow of this Bayesian analysis. So here I've cropped the flow charts in the slides, and it will remind you that what each section of this notebook is doing. So this first few blocks will first define the parameter space with prior knowledge, and then run the toy model on a finite set of the predictions. And this set of predictions will be used for training the emulators. So in block 4, that's we'll define the names of the parameters. So these are formatted strings used for later plotting scripts. And this is the range. The normalization will vary from 6 to 15. The kink value of the shear viscosity is varied from 0.02 to 0.2. The high temperature slope, actually include units over here. They are in units of 1 over GeV. This is 1 over GeV. And finally, this is units of GeV. And the low temperature slope is from 0 to 10. And the location of the kink is T. That's temperature is varied from 100 MeV to 400 MeV. And we're going to run 200 design points. We were going to run the toy model at 200 design points. And so here we will see another flag. So if this flag is true, then it will load the pre-generated design. So this design are generated from what we call Latin hypercube design. Is a very specialized sampling technique. I'm not going into the full details over here. But just in one sentence, so this design will at one time randomly samples your parameter space, but also try to maximize the distances between any parameter points so that it gets a better space filling features than pure random sample parameter points. So we're going to directly read this design file right now. And when you have time, you can turn this to false, and then it will show you how to, for example, call the Python implementation of this experimental design, this Latin hypercube sampling, and then how to generate a new design for other purpose. Run through this block. So it load design from file. The design shape is 200 by 5, means that there are 200 parameter points. Each one contains a 5-dimensional parameter vector. And block 5 and 6 will just show you what this file contains. So first is the range for parameter 0 to 4 or 1 to 5. This is the maximum and minimum range of each parameters. And in block 6, it's print out the first 5 design points. So this numbers looks looks like completely random, but actually it's not completely random, as you will see in block 7. So block 7, again, we will call this hist1d and 2d function to check what the design looks like. So right now I'm plotting the design of the first parameters, or actually it's really the second parameters versus the third parameters. And here you can see that on this 2D plot, it looks quite random, but if you look closely, no two pair of points are really close together. If they're really close together, they will also have a gap in another dimensions. Furthermore, if you marginalize the design points to one dimension, it's exactly a uniform distributions. So this is very different from a grid design. So in a grid design, you are only going to pick points on, for example, equally spaced x and y grid, which will marginalize to a few delta functions in one-dimensional distributions, and they will be tightly clustered in these two-dimensional distributions. And the worst is that if you use grid design, the number of design points that we're going to run your model will explode exponentially with the dimension of the parameters. While for this like semi-random Latvian hypercube design, for smooth enough functions, you will only need like a linearly increases number of design with the number of parameters. So right now we have 5 parameters, but we have 200 design points. So that's 40 design points per dimension. So after this, you can also check what happens if you vary the design points, and when does your analysis get stable? Because we have seen the previous examples, number of design points really contributes a lot to the uncertainty. Okay, and then step 2 is straightforward. Just run through the toy mode, run the toy models through every design points in the design. So this may take either a few seconds or no more than a minute on your laptop. So it loops through each of this loop over the 200 design points, and then compute that toy model. So this toy model will return a vector of number of charged particles and another vector of V2, and we'll concatenate them together into a single vector. So that's in total 10 numbers, I think 5 for uncharged particles, 5 for V2, to represent the simulated observables at 1 parameter point. So eventually you will get, let's print out the shape of this simulation. Okay. Yes. Oh, sorry. It's actually 8 centrality points. So at each one of the 200 parameter space, you get 16 predictions, and the first 8 will be in charge, and the last 8 one will be V2. So this is the first step: design plus running model on the design points. And from step 3, it will be the new stuff that we're going to use, the emulators. So this finite set of model predictions will be used to train emulators. But here there's another additional stage. So this stage is to some extent optional. because if you have only a few predictions that are not so correlated, then you don't really need to do this dimensional reduction step. But here we have 16 of them, and we know they're strongly correlated. So we have this extra step. So here's a short motivation of the dimensional reductions. So there are many dimensional reduction techniques, but the one we're going to use over here is called principal component analysis. So generally speaking, it's a quite systematic way to find features in high dimensional data. For example, right now we have it's actually 16 values of the uncharged data and V2, and we know that if we tune up the normalization, then all the centrality, the charged particle number in all centrality bins will increase, and if we change the shear viscosity, the V2 of all centrality will change accordingly. So we don't need 16 numbers to represent this change. Instead, we're going to decompose them into linear combinations. For example, one of very easy linear combination is you take the average of the uncharged particles for the 8 centrality bins and use the average to reflect a more direct relation between particle production versus the normalizations. But I mean, this average is just a linear combination that comes up from our instinct, but this PCA will be a systematic way to convert our instinct of how this parameter correlates into truly second moments independent, uncorrelated features of the data. So to demonstrate this idea, we can take, for example, in this case, the charged particles and V2 in the first centrality bins. So block 9, it histograms that 200 calculations of, on axis, the uncharged data in 0 to 5% centralities, and on y-axis is the V2 from 0 to 5% centralities. And what PCA does is we'll try to find the principal axis of this two-dimensional distribution and try to use the new coordinates defined along the principal axis to represent the data points. But of course, you can only define a principal axis in a very efficient way when your data, when the joint distribution of the two observables looks kind of like a normal. But in this case, the V2 and the uncharged data kind of look like there's a banana-shaped correlations. Further, if you marginalize V2, the distribution is not a normal at all. It's a very skewed distributions. So usually before applying PCA, I will also try to find another nonlinear transformation that makes this observables, makes them correlation looks kind of like a Gaussian. So in this case, what I'm doing is take instead of emulating the uncharged data and V2 directly, I will emulate the square root of these values. Because if you plot the square root of the uncharged data versus the square root of V2, of course, it's not a perfect Gaussian distribution, but it's definitely more close than this banana-shaped distribution. So in the rest, we're going to build emulators that emulate these quantities, and then we can always transform from the square root of observables back to the original observables. Of course, you can also you're free to try what if we don't use this nonlinear transformation, set this to false, and then if we use the simulation data instead of the square root of the simulation data. Right now, let's set this flag to true. And another thing that we need to do before applying either PC or Gaussian process emulator is to standardize the data, because often in your predictions you have observables that differ in orders of magnitude. For example, the chart data ranges from 1,000 to 5,000, but V2 it's a number of a few percent. So if you put such numbers separated by such large of scale into any algorithm, then you're either going to lose accuracy of the very large number or the very small number. So before we do that, we will make another transformation that's called the standard scalar, which will subtract all the data by their mean and divide it by the standard deviation. So after this transformation, the observables will be balanced around plus and minus with typical variance of unity. This is very important if you want to apply this analysis when your predictions contains observables that are either contains very large numbers or very small numbers. And then in block 13, it applies this principal component analysis. Again, I will not go into the details of the math of how this transformation is defined, but instead, I will just leave a few port where you can tune some of its internal parameters. So the first one is this number of principal components. So this is the dimension of the features that we want to keep for that 16-dimensional parameters observable space. So remember that we have 16 observables and 8 in charge and 8 V2. And this number of PC is the number of features that we really want to emulate.
Weiyao.
Yes.
There's a question on Slack. So how do you? So it's about the earlier part. So the question was, how did you choose the square root? Is finding the right transformation a matter of trial and error, or is there some strategy to it? Was referring to a previous block, I think.
So actually, yeah, of course, square root is this kind of arbitrary, but often when I do this analysis, the criterion is that this joint distribution should not contain a significant degree of nonlinear correlations. So nonlinear correlations that are not well approximated by multivariate normal, which is kind of the basis of the PCA, the principal component analysis. So the first thing I do is to check these joint distributions, and if there's some very strong nonlinear correlations, I will try to think of ways to get rid of it. In this case, you can also try log. Let's see. Well, seem to work.
For different power, right?
Yeah. For different power. Yeah, but of course, these are not always, as you say, unique. Especially, we're only checking the pairwise correlation of one centralities, and I haven't checked other centralities and other combinations. So this will, I mean, this eyeball type of approach will quickly get out of control when you have many different observables. So maybe when you make one of them looks okay, maybe you break the correlation of others. So I'm not sure whether there are systematic ways to do this, but we can keep looking. But I think in generally when there's a strong degree of nonlinear correlations, there's no unique way to get rid of them. Okay. Now I've changed back to I have to change it back to square root. Okay. And so this number of features, so usually it's enough to keep just a few of them for the reasons that going to show up very soon, and then it will define because this transformation are essentially just linear combinations of the original observables into three new principal components. So this principal components Z are just linear combinations of the charge and Weiyao taking care of their natural correlations. And because they're linear transformations, we can define the inverse transformation matrix that simply takes a column of Z vectors back to the charge and Weiyao. So how do we know that three features are enough? Three features are enough. So if you run through block 14, this is something very important to check when you apply dimensional reductions. So on the horizontal axis is the index for each feature or the index for each principal components. So each one will correspond to the coefficient in front of the linear combinations of the observables. On the vertical axis in the first plot is the relative importance of this particular linear combinations. So in this case, this algorithm has already ordered all the principal components in a descending order. So you see that the first principal components is really important. So usually will correspond either to the mean of our data, so something like a mean of our data. And the second will start to include some features like generalized slope or generalized curvature in the data. You can actually visualize what these principal components look like to see what they're actually doing. We'll see if we have some time to do this at the very end of this notebook. And on the right is the cumulative importance. So after you include the first three principal components, you're already taken care of almost 100% of how prediction varies with respect to the input points. So that's how we know that three principal components is enough, and the fact that all the higher principal components almost contributes nothing to the total variance of the data is also basically the reason that the dimensional reduction is possible. Okay. So now it comes to the training of Gaussian process emulators, which we have been talked a lot today. Before we do that, please notice that there is a override flag. So if it's set to false, then it will directly load an emulator that I have already trained and is packaged with this GitHub repository. You can do that if if the training is taking so much time for you. But here I'm going to retrain this. So set this to true. Once it's set to true, then it will build a list of emulators, because now instead of just emulating one quantities, we actually have 3 quantities. The loop over the range of number of principal components, and for each of them, just like the previous example, we will build a kernel for this Gaussian process. It includes a radial basis function and also a white kernel. So this white kernel is important when when your model is not deterministic. Of course, in this case, our model is deterministic, but for general purpose, it's important to include this. For example, in your Monte Carlo simulations, the calculations may deviate from the true deterministic predictions at a particular point, and it's possible to include these features in the training of the process. So whenever you have included the white kernel, the Gaussian process will know that it doesn't have to pass through every point that you provide exactly, because there are statistical fluctuations in your calculations, and they'll also try to optimize this other hyperparameters, the noise level, to balance between the interpolation and also how much percentage of the data it is considered as noise. And if you run log 15, it will start to training the emulators. The training time will increase rapidly with the number of design points, but right now there's only 200 of them. It's taking a few seconds. Actually, if I don't have Zoom running right now, it will take even, I think, it would be less than one second. And the score for describing the training data is also looks good, but as I said, it's always important to do validations. So the validation is basically you sample new parameter points where you have not trained the data, and compare how the emulator predicts observables at these points versus the true model calculations. We will do the validations in a minute. And then in block 16, because these notebooks involve the PCA that I didn't go into full details in this lecture. So in this block 16, I try to package its features into single functions. So this single function is the one that we're going to use over and over again. So that's basically what all these 4 steps is doing, from parameter space to emulator to dimension reduction, its inverse transformation to finally make the predictions. It's all packaged in these single functions. So it wrapped some details that we don't talk about. So this function will take the model parameters, and also you can choose whether to return the covariance matrix or simply returns the diagonalized the diagonal components as the standard deviation of the predicted quantities, and inside it it will loop over each principal components to generate predictions at this parameter point, and then it will inverse transform from the principal component space by that inverse transformation matrix that we defined back to the physical space. So at this point, okay. So the first step is from parameter space to PCA space via the trained Gaussian process emulators. And the second step is from PCA space to the square root of V2 and the square root of uncharged particles via inverse PCA transformation. And this last step is, in case you have turned on this nonlinear transformation flag, it will transform square root of observable back to observables. And notice that in the meantime, the variance also changes. And finally, depending on your purpose, you can either return the mean prediction plus standard deviation, or return the mean prediction plus the full covariance matrix. Okay. And the final step is to validate that this emulator really works, just in case of overfitting problems. Okay, so this for blocks and these three steps is basically what this predict observable function is doing. And we want to test that it also works for novel parameter sets. So in block 17, notice that I have set random numbers. So in principle, we should get similar results. We're going to sample 2 novel parameter points from the design range. So as you see, this is just a way to generate 2 random points within the design range. This is the minimum plus 2 random numbers from 0 to 1, and this design dash P2P is actually the length scale. So this number is simply the design max minus design minimum. So samples 2 additional parameter points, and then you can make the prediction for each of them. You iterate over each of these 2 parameter sets and use that predict observable function to get predictions, and we also want to return the standard deviation of the predictions. And then we can split this prediction into the center prediction values and the standard deviations. In the meantime, we want to make sure this prediction
Weiyao, you seem to be muted.
Oh. Wait, how long have I been muted?
Maybe 20 seconds, 10 seconds.
Hello?
Yeah, so
Okay.
not very
Can
long. Yeah, maybe 10, 20 seconds.
Okay. Okay, then I will repeat for. Okay, so I think that's where I am. In the predict observables, we will loop over this newly generated design points and predict the values of uncharged and V2 at these points, and also the predicted uncertainties characterized by the standard deviations. And to compare, we will also compute the actual model prediction at these 2 parameter points. They are stored in this Y validation. And then in the following plotting block, it will compare the model calculations versus the the emulator prediction with the uncertainty band. So here you can see the mean minus standard deviation and mean plus standard deviation. So it's 1 sigma band. And you run this block. You have a plot like this. So in this case, the blue dots are the actual model calculations at these 2 parameter points. And the red band is the mean plus 1 sigma band of the emulator predictions. So it's doing quite well in capturing the data with quantified uncertainties. You can try other points. For example, you can change the random number to 4. Yeah, so this corresponds to another set of parameters. You have a change shape of V2 versus centralities, but still you you kind of capture this change also in the emulators. So let me see if I can find some cases where this doesn't work. Okay, seems like a good emulator. Okay. So here you start to see something that you didn't expect, is that when your V2 is dropped very close to 0, the emulator seems to predict something something strange, because I mean V2 has to be positive definite, and in this case you are probably very close to the boundary of your design. For example, one of the boundary of the design is that you have very large shear viscosities, and whenever your Gaussian emulator is close to the boundary of the design, because on the other side of the boundary you don't have much training data to constrain the behavior of the emulators, so uncertainties is going to be large at the boundary. So whenever you make this, you really have to make sure that the design range is large enough so that you always have a good emulator performance within the area of interest. But of course, in this way, we can really only test a few points to make sure that it works globally within the parameter space. We're going to do a more systematic test. In block 18, we will generate 100 design points, novel design points within your parameter space, and basically do the same as the previous block. On the one hand, we generate the validation data from the model. On the other hand, we generate the emulator predictions with uncertainties. But this time, we want to see not just that the predicted values are close to the validation values, but also we want to see whether the uncertainties are correctly estimated. Remember that Gaussian emulators, when marginalized on a single quantity, should be a Gaussian itself. So we will check this self-normalized discrepancy factor. This delta is defined as the emulated y minus the model prediction of y divided by the standard deviation that's being emulated. So this should be order 1 quantity if the uncertainty of the emulator is correctly estimated. So we're going to histogram this delta factor for all the data points and all the observables that we're generating. Okay, it's going to take some time because it will run the model another 100 times. Yeah, and this is what you get. This is the discrepancy factors, the distribution of this discrepancy factor, and it's also compared to the standard normal distributions. So it's not far from the standard normal distribution. Of course, it's somehow it's a little bit narrower than that. But whenever you see this distribution is so different from a normal distribution, then either it means that there's something wrong with your validation, or the Gaussian or the training or the Gaussian emulator doesn't estimate its uncertainty correctly. Okay, I know this is another ton of information, so I guess we can take another 5 minutes break before we go to the final step of Bayesian inference. And in the meantime, you can ask questions about this first half of this notebook.
Sounds good. So we will be back at 11:29.
Yeah, thank you.